Okay, let's start the last session for today. And okay, before beginning, so we've seen the case of divisible resources, which we saw yesterday, which we've been modeling as a cake or a segment 0, 1. Then today we started with another notion of resource where it can be an indivisible setting, which means that a resource cannot be divided, as was the case with cake. And in that particular setting, we saw that, envy freeness to begin with we cannot really guarantee. And so we went on to define EF1 and such notions. But so in this particular session, I'll introduce you the third landscape, which is indivisible setting to begin with, but in presence of some divisible resource. So it's a case where you have both indivisible goods plus some divisible resource. Yeah. Indivisible setting in the presence of divisible resource. Okay. So in this lecture and some lecture tomorrow, we will focus on this particular setting and note that, so again, colloquially it's been termed as the problem of rent division. In a moment, I'll tell you why is it called so. But okay, let's assume that there are a bunch of friends, let's say n friends, and they all want to share an apartment having n rooms, and they need to, okay, so this apartment basically comes with some total rent, and they need to divide the rent into amongst themselves such that every price comes up with a rent, and they also need to allocate themselves to these n rooms such that again this particular division is again envy free. I'll be formal in a moment. What do I mean here? Okay, so divisible resource here is nothing but you can think of it as money, which can be divided fractionally. An indivisible resource here is a room. So exactly one agent or exactly one friend needs to be assigned to one particular room, and we need to also impose a rent on a room or a price on a room. Okay. So let's say sigma. Okay, so let's say we have set of these n agents denoted by A, set of these rooms denoted by curly R, and I want to come up with a matching or an assignment sigma from this particular set of agents A to the set of rooms, and coupled with this particular matching, I also need to come up with a price vector P, which must reside in Rn because it's price of all the rooms, so P1, P2 till Pn, such that I achieve envy freeness again, such that following happens. So again, for achieving envy freeness, I need to define what a valuation function is and everything, but again, let's just assume it's denoted by, okay, in this particular lecture, I'll denote it by utility, U, because there's a money they'll also pay, and therefore, what is the utility they're getting out of being resided in this particular room. So utility, utility of agent A for room he's being assigned, which is sigma A, and also paying a rent, which is P of sigma A. So, okay, this notation is clear. Utility an agent A is deriving if he is assigned a room sigma A, and therefore he pays a rent of P of sigma A. So let's say sigma of 1 is 7 or something like that. So it would be utility and agent 1 is deriving when he resides in, let's say, room 7, and also pays the rent for room 7, which is P7 in this particular vector. Okay, so currently I'll be denoting this as my utility vector, utility function. Okay. Okay. So this is the utility an agent A is deriving if he's assigned this particular bundle, and again I'll denote a bundle as a room along with its price. Okay, this is a bundle for me. If he's being allocated this particular bundle, and let's say I'm right now focusing on the fairness notion of envy freeness, what do I write here? Again, so he shouldn't be envious of any other friend. Again, under the imposed rents P. Okay, so it should be U of A, sigma of anyone but louder. Yeah. Yeah, just say it. Yeah, okay, so any other room, so sigma B, but which again I can write as, let's say, R comma PR, right? Any other room. Sure, it will turn up in sigma B or as well, but just for notational ease, I can write as this. So for all rooms R, and this happens for every agent. Okay, this is a notation, but okay, for all rooms and for all agents A. This is coming from the set A and this is coming from the set R. Okay, so this is the notion of envy freeness I am after. Okay. So I need to, okay, currently I have two things at hand. So till now I just needed to have a partial allocation or an allocation of a cake and divide it. Right now I need to come up with a price vector on each room and also an assignment of agents to room, and here exactly one agent gets, so exactly one agent is being assigned to a particular room. So coupled with this, so okay, in this notion this is my allocation currently, or a solution. So a tuple sigma comma P, where sigma represents a matching and P represents the imposed rents on those end rooms, is said to be envy free if something like this happens. Okay, I should have. Yeah, okay. So is the setup clear? I was a roundabout. I defined it in roundabout manner, but just let me go through it again. So currently an allocation or a solution would be defined by a tuple sigma comma P. The first entry sigma represents a matching, which basically assigns every agent to a particular room, and the second entry, which is the price vector P, resides in the Euclidean Rn domain, and it is said to be, this particular tuple is said to be envy free if the utility agent A is deriving from residing in, let's say, the room sigma A and paying rent, which is the assigned rent for this particular room P of sigma A. It must be at least the utility he will be deriving from any other room under the same imposed rents P. Okay. Again, like, I am hoping this notation is clear. PR just represents rent of room R. Yeah. And sigma A means the room he is being assigned under the matching sigma. Okay. Yeah. So the problem again is first existential question. Do such an allocation even exist? Like finding an envy-free allocation or a solution such that something like this holds true for all agents. Okay. So is the setup clear? Right now we are having indivisible resources which we term or which we call them as rooms, and coupled with them is a divisible resource which we again say, let's say it's money or something like that. Yeah, yeah. Yes. Yes, so it's the utility function. So you have a utility function defined for each room for every possible price P. Yeah, so when you have this particular sigma comma P at hand, how do you calculate if you're being NV free or not? You just calculate the utility you're getting from your room under the rent which you are paying for that room, and then you calculate utility you would achieve from some other room under the imposed rents, which is R, PR is the rent for room R. Do I answer your question or did I not get it? Yes. No. You need to take account of the price also coming along with the room. Yeah. Yes. So again, the bundle is R, PR. The price is attached now, okay? And in this particular problem, you need to find both, like sigma and P, such that this happens. Yeah. P is also in our hands to compute, but first is the existential question. Yes. Yeah, that is one assumption we can have, but we'll circle back to that assumption. Yeah. Yes. Yeah, I'll tell you the assumptions we'll have in a bit. Yeah. So they're like basically two models of valuations I'll discuss, and therefore I've not yet told. Yeah. Okay. So is the problem clear? We are having indivisible resources along with some divisible resource. Okay. Okay. So let me talk about the existence question. So does there exist an NV-free allocation? NV-free, let's say rent division is what I'll call NV-free rent division under some assumptions, which I'll tell you, under some assumptions. Okay. Yeah. Okay. Yeah. So again, I'll like you all to recall Sperner's lemma, which was covered yesterday in the last session, and I'll see if I can the way we used to prove existence of NV-free K-cut, can I again somehow use it to prove existence of NV-free rent division using Sperner's lemma? Is it possible, and or will I fail the way I failed for burnt cake? Okay. Yeah, okay. So let's say this is my model. Let's say this is room 1. Again, I'll work with n equal to 3 again for ease of presentation, and we'll see if what happens for greater number of agents. So let's say there are 3 rooms and 3 friends or 3 agents in the system, and let's say this is the price for room 1 is P1, this is P2, and this is P3, and we want all these Pi's to be greater than equal to 0 for all i's in 1, 2, 3, and also we want, which circles back to the total rent condition, let's say I do want total rent to sum up to 1. This is what I want, let's say, okay. So again, as we saw yesterday, let me consider this particular triangle. Let's say this is the point 1, 0, 0, this is 0, 1, 0, and this is 0, 0, 1. Let's say, okay, just consider this particular space as a space of prices. I'm trying to have a graphical representation on the set of all possible prices. So again, as we saw yesterday, there are 3 extremes. Room first is the one which has to pay the whole rent, which is 1. And this is the first extreme, and similarly we have 2 other extremes, right? And since this is the equation I do want, I know that every possible price you want to have, which is, let's say, this particular p vector, resides in this particular plane, which is a chopped off plane sitting in first or 10. Okay. So is it clear that every possible price vector is being represented by this particular triangle, right? This is again clear. This is again exactly the way we did it yesterday. Okay. And also, why are we having pi greater than or equal to 0? Because we really don't want, let's say, I don't want you to pay to live in a room. You must be paying. You are a payee and not the other way around. I want people to pay to live in a room. Okay. So again, so these are some assumptions I'll have on preferences or utility functions. So again, as we saw yesterday, the first one is like for every price p, so for every price vector p, and let's say again we have 3 agents in the system A, B, C. 3 agents, 3 friends, whatever you want to consider. Okay, so the first assumption is for every price vector p, every agent, by which I mean so agent A, B and C, all must be able to pinpoint to, okay, so under this particular rent allocation, I would want to live in that particular room. This is the room which gives me highest utility. So every agent again must be able to tell his favorite room. Okay, this is again the same thing which we had yesterday, and the second assumption we will have is a free room is preferred over a, let's say, non-free room. This is similar to the hungry condition we had yesterday. So even if this might seem a little off, but that's the assumption we are having right now. Every agent just wants to, if there's a room which is coming for free, he'll just want to live in that particular room as compared to any other non-free room. Okay, if there's a way of just living in a room for free, he would like to choose that particular option. So these are two assumptions I have, and again, as we saw yesterday, I'll have the assumption of closeness of utility functions, just to have the limiting argument as we saw yesterday. Okay. Oh, price free, a free room as in, okay, a room with rent 0. Let's say if any room for any room pi is 0, that room would be preferred over any other room pj if, let's say, pj is greater than 0. Yeah. P, which means that this p of this particular room is 0. And non-free room means that there's a non-negative, there's a positive, strictly positive rent you need to pay over here. Okay. So this is the model again, and let's see what we can do with this thing. Okay, can someone tell me now? Okay, no. Okay, so again I'll have that ownership labeling as we had yesterday. I wish I could copy it, but. So again what I'll do is, I'll consider some triangulation of this particular triangle and have an ownership labeling. So let's say the owner of this particular vertex is A, and the owner of this particular vertex is agent B, and similarly here it's agent C. So, and that's how I complete this ownership labeling. ABC. Hmm. Where am I going wrong? Okay, let's just have, yeah, okay, fine. Okay, so this is one of the ownership labeling you can have, and let's do the same exercise which we did yesterday, and I want you guys to tell what would be the labeling. Just what? No, this is an ownership labeling and not a spawner labeling. Yeah, just again, yeah, this is just an ownership labeling. Okay, let me recall what an ownership labeling is. By which I mean that every elementary triangle, if you just consider the vertices of these three triangles, all three agents must appear exactly once. So therefore it's known as ownership labeling. You have representation of every agent in every elementary triangle. Okay, it's okay. This is not a spawner labeling. I'm not at all I don't want it to be a spawner labeling. It's just an ownership labeling. Yeah. So if you can again eyeball it and just look here, every elementary triangle, just look at all these three vertices. Let's say in this particular elementary triangle, I look at all three vertices and I can see that there exists exactly one agent on exactly one vertex, right? Yeah. So spawner labeling will come now. Okay, can someone recall what were the conditions for spawner labeling? Yeah, 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 exactly. So we wanted, okay. So just to recall, what I want is this particular, let's say all three main vertices must get distinct labels, and over here the labels must be 1 or 2. Here it should be 2 or 3, and here it should be 1 or 3. And for the labels corresponding to the inner vertices, it can be arbitrary, right? And what does Spanner's lemma asserts? It says that exactly there exists exactly one fully labeled elementary triangle, right? That was our Spanner's lemma yesterday, and let's see if we can just apply it over here. Till now it seems all good, but let's see. Okay, remember this was the vertex 1, 0, 0, and yeah. Yeah, okay. So let's say this is, so this represents the price vector. Okay. So can someone tell me what would happen? Let's say I go to this particular vertex and I see who's the owner of this particular vertex. It turns out it's agent A. What do I ask him? I ask him, okay, at this particular price vector for 3 rooms which are indivisible, but just tell me which is the room you prefer the most. What will be his answer? First and third, right? It is not second which we wanted, but fine, okay, let's just see. It's either label 1 or label 3, right? He'll label this particular vertex either 1 or 3, right? Similarly, I go to this particular vertex, go to my ownership labeling, see who is the owner, it's agent C. I ask agent C the same question again, and what will be his answer? Yeah, second, he'll either label it 2 or he'll either label 3. Right? And similarly here it will happen, it will be again either 1 or 2. Yeah, okay. Can now someone tell me what will, let's say, happen on this particular edge? So if I go to these particular 3 boundary vertices and ask the corresponding owners, what will be their answer? Exactly, right? It would be, they'll always say that, okay, I'll label it 2, 2 and 2, right? Because it's the second room which is coming for free. They will all want to live in that particular room, and that's what we've assumed, right? They prefer a free room over a non-free room, right? Similarly, what will happen on this particular edge? Yeah, exactly. It will all be 1, right? And similarly, this will all be 3. So it doesn't really look like a spurner labeling. It's not, right? Okay, because for spurner labeling, what we wanted, all the main vertices to have distinct labelings and choices on the edges. Here we have choices on the vertices and fixed labels on the boundary vertices, right? So it's not spurner labeling, but I don't know. Let's just apply the path argument. Maybe it can work, right? Let's see. Okay. Let me just have, okay, here I'll just have some, let's say some arbitrary labeling. Okay. So what was the path argument? I started with a 1-2 door, right? Here also I'll start with a 1-2 door. And I enter this particular house through this particular door and continue my path. Either the room I enter via this particular door will have, let's say, the third label and I'm done. And otherwise, what I'll do is, what I'll find is another door and from which I can exit this particular room and enter another room and continue doing it, right? And remember, this path can circle back and we can be thrown out of the house, but there'll always be one more door from which we can enter, because we've seen that there are odd number of doors and such. But is it all true here as well? Let's see. So I'll just do a case analysis and I'll try to see if the spurner path works or not. It might not. Let's say for case 1, this particular label is 2. I had an option 1 or 2. I'll do both of it. Let's say it's 2 right now. So do you see a door 1, 2 anywhere? Yeah, exactly. So let me enter this particular room. Okay, so this is a door, and there exists exactly one particular door, right? So just enter from here, and I do the path following argument. I keep on doing it, and okay, I do reach. Huh. Yes. Oh, okay. Okay. I had to stop here. Okay. Yeah. Good. Thank you. Okay. So what happened is there is exactly one particular door. So there is no way I can be thrown out of this particular triangle, because there is no 1-2 edge on any other boundary, right? There's no, if you can just eyeball and see, there is exactly 1-2 edge on the whole boundary of this particular triangle T, right? So since this is a finite, we have this finite number of elementary triangles or these rooms, I'm sure that this path will terminate somewhere, and it can terminate. The termination condition is exactly the termination condition is that we'll be able to reach a fully labeled elementary triangle, right? This is the illustration. I entered via 1-2 door. I followed the path, and I know that I can't be thrown out of the house, which means that I'm bound to terminate on a fully labeled elementary triangle, right? So is this path following argument clear again here? And you can do the same here again. If this particular label was 1, this will become the door, and then do the same argument. It will be just you enter from here and you follow the same path, right? Yeah. Yes. So, okay, so what? No, okay, but I really don't know what they are answering, right? You are restricting the answers of, let's say, these players, right? So, okay, are you saying that let me have 1 here? Okay, I see what you're saying. We can force him to label it 1. We can again force him to label 2 and this, let's say 1. Then just, Got it. Yeah. Then you will definitely come up with a Sperner labeling and follow the argument. Yeah. That also works. Yeah. Correct. Okay. So here also what we saw is via Sperner's lemma, once again we were able to prove existence of an envy-free Renn division, right? And again, it's again a limiting argument, and we'll be able to, okay, how will we define sigma, the assignment sigma? So, so the limiting point, let's say this is the limiting point P of this particular sequence of triangles, and at this particular point P, I know that every agent is preferring a different room, and that will just induce a sigma, right? And that will be the vector P, and sigma comma P will give me a envy-free Renn division. Okay. So is this clear? Yeah, this is fairly easy argument once we have seen yesterday's argument. Okay. So in a way, argument is, in a way, like the intuition is, even if you have indivisible resources, but if you have divisible resource, money in this case, to compensate envy, you can guarantee to, you can say that, okay, envy-free allocations once again exist. If you can just compensate that envy with money. Yeah, okay. Any questions in this particular part? So yeah, just to complete this particular theorem, it says that an envy-free Renn division exists under these three assumptions. And the existence comes again via Sperner's lemma. Right. So if there are no questions, I'll move on to second model of utilities in this particular setup, which is Renn division, and we'll see what happens over there. Yeah. Okay. So, okay, again the problem is the same, to find envy. Envy-free Renn division. Okay. But what we'll do now, we'll have another utility model, and we'll see what happens in that particular utility model. Yeah. So again, a Renn division instance is, you have a set of agents, you have a set of rooms, and then you have some utility functions again for each agent A, and for each agent A, you have a utility function for each room at every possible price. So I'll again, yeah. So this particular function represents utility, and it takes a price vector and spits out the utility of this particular agent A for this room at this particular price x. Okay, so this is a function going from R to R, and you can think of x as the price of that room R. Okay, yeah. Okay. So to begin with, I'll have one model of utilities, and then at the end we'll see that if we can generalize that particular model. So this is known as quasi-linear model. So quasi-linear utilities. Okay. Yeah. Yeah. So how do I define a quasi-linear utility? It just means that, okay, so this particular utility for, let's say at a price x is defined by, so this particular agent has some base value for this particular room, and I'm denoting it as, let's say, VAR minus x. So he has this threshold value that, okay, he is willing to pay this much amount of money for this particular room R, and his utility is nothing but just subtract this base value, subtract the price of this room from this particular base value. That's what we call a quasi-linear model. Okay. Yeah. So if you want to see it graphically, what happens is you start from this particular point and then it decreases linearly with slope -1. And it becomes 0 at exactly VAR. And this is the utility function of agent A for room R and for a price which is, oh, okay. So this is the X, which is the price of the room, and here is what I'm getting utility. Let's say this, okay. So it's a quasi-linear utility model where you have some base value for a particular room, and this base value might change with distinct rooms, and what you do is you just subtract the price you are paying for that room, and that is your utility from that particular room at that particular price. Yeah. Okay. Is the utility model clear? Right? Okay. So again, just to reiterate the definition of NV-free Renn division, I say that an allocation sigma comma p, where remember sigma is a matching or a bijection from the set of agents to the set of rooms R, and again I am assuming that, let's say, this particular thing is N. You have exactly same number of rooms as the number of agents. Yes. Oh, because you have -1 here, right? It's decreasing. You are it, right? Yeah, okay. So higher the price you pay, your utility goes down, right? So the slope is -1. This is a fixed constant for this particular pair A and R, which is this. Yeah. And the utility becomes 0 if you're paying that much price for that room. If you're paying whatever your value was, you just get 0 utility out of it. If you are made to reside in that room, okay? Okay. So an allocation sigma comma p, it's a tuple sigma comma p where the first entry is a bijection from A to R, and the second entry is a price vector which denotes price for each of the n rooms. Okay. So an allocation sigma comma p is said to be NV free if, okay. Can someone tell me what happens? What's the NV free constraint I need to write over here? Yeah. We've seen, I've told you the definition of NV freeness in the first slide. Yeah. So, okay, so what I'm asking is, what should I write? An allocation would be NV free if what happens? Yeah. 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 So mathematically I can write it as, yeah, okay. So UA getting room sigma A at price sigma A must be at least the utility he is achieving from any other room at the particular price, which is under the imposed rents, which is P. This happens for every agent A and for all rooms R. And I can again write this particular NV-free constraint as something like this: VA of sigma A minus P sigma A, because that is the utility model I'm assuming, which is quasi-linear. This is at least, so this utility he's deriving from his assigned room sigma A is at least the utility he's deriving from any other room at that price, at its own price, right? So this happens again for all A, for all R. Yeah. So this is the NV-free constraint, right? Yeah. Yes. Oh yeah, again, once again, so as I said, like this particular base value can change with different rooms, right? So even, yeah, it can change. So this is not a universal constant, it depends on A and R, right? For this pair, it's different. Yeah. So this is the Renn division instance we are looking at. This is the particular utility model which we are focusing on right now, and this is the fairness notion I want out of this problem. Okay. Any doubts in the model or the setup? Yeah. So if not, I'll move forward. Okay. So again, this is the setup pictorially. You have bunch of agents A, and then you have equal number of rooms on the other hand, right? So what I'm going to construct here is, let's say, a valuation graph or value graph. I'm saying it, why am I saying it a valuation graph? It will be cleared. Remember, this is the value I am saying. This is the base value for an agent A, base value of agent A for a room R, right? So what I'll do is I'll construct a complete bipartite graph. Okay. So I have on one partition I have all n agents, and another partition I have n rooms, and it's a weighted graph, by which I mean that, let's say, the weight on an edge AR, let's say this is agent A and this is room R. So this particular, so I have some weight on this particular edge, and that weight is nothing but his base value for this room, so VAR. Okay. So what I have constructed is a complete bipartite weighted graph. Okay. So why is it complete? Because you have all n agents going, n edges going from each agent to each room. Yeah. So basically you have all possible edges. Yeah. So can someone tell me how many edges do I have in this particular graph? N into R. No, n into n. It's this. Yeah. So okay, I shouldn't write here, but I have this particular thing, right? I have exactly same number of agents and same number of rooms. So I know that the number of edges in this particular graph, and let me call it as G. Okay, and let me call this particular instance as Q, and therefore let me call it as GQ. So number of edges in this particular valuation graph for a given Renn division instance is n square. Okay. And I have said that just give a weight of VAR to each edge AR. Okay. This construction of valuation graph clear? Okay. Okay, moving forward, I would want to define one particular term which is maximum weight perfect matching. So, how many of you do know about this particular term? Have you, yeah, okay. Have you ever heard of maximum weight perfect matching? Okay, let me define it. So, it just means that you have this particular graph with you and you want to find a perfect matching, by which I mean that every agent must be matched to some particular room and you want to maximize the weight of this matching. So, if I want to write mathematically, what I mean is I want to maximize, so I want to maximize VA of sigma A, let's say sigma is the matching, and I sum it over all agents, right. So, this is, okay, I should have, let's say, some example. So, let's say I have 3 rooms and let's say I have 3 agents, and let's say these are the values, these are the base values, let's say something like this, 5, 2, 1, 4, 1. Okay. So, let's say this is the valuation, this is the base values. So, agent A1 have value 9, has a base value of 9 for room R1, base value of 4 for room R2 and base value of 3 for room R3, okay, and so on. So, what do I mean by maximum weight perfect matching? I just want to come up with a matching which should be perfect and I want to maximize the weight. And remember, the weights are nothing but these matrix entries in this particular graph, right? Yeah. Okay, louder. There's no price right now. Base, okay, maximum of base values, yeah. No. Yeah, okay, yeah. So I want, okay, okay, first of all, tell me how many matchings can I have in this particular setup? Yeah. No, number of edges is n square, but number of total matchings, perfect matchings. Yeah, exactly. There are n factorial possible matchings, right? And I'm denoting a matching by this sigma, okay. So what I want is, I'm saying that, okay, pick one particular matching sigma and compute this particular value, that VA of sigma A, and then sum it over all agents. This is the value of this particular matching sigma, okay. And then what I'm saying is maximize this particular value over all possible matchings. So you have n factorial matchings, you compute this particular value for sigma 1, sigma 2 till sigma n factorial and you take the maximum of it, okay. Yeah, so basically argmax of this particular quantity would be the max weight perfect matching which we are looking for, okay. It would be clear in a minute why am I defining this particular term. But yeah, so in this particular illustration, can someone tell me, uh, do you find a max, can you tell me what is the max perfect matching, max weighted perfect matching here? exactly. So we have this, right? Yeah. So so this is the max weighted perfect matching. You can also let's say see for this particular thing, right? Something like this. For the first one, the value is how much? Like the green matching, how much is the value of this particular matching or the weight of this particular matching? Yeah, it's 18, right? So so the weight of this green matching is 18. Can you tell me what is the weight of red matching, which is this, right? It is 7, which is indeed lesser than, indeed lesser than 18, right? So that's what I mean. You go over all possible matchings. Here it would be 3 factorial, which is 6, and then you find that particular matching which has maximum weight, right? And this is so this particular quantity is the weight of matching sigma. And then you maximize this particular quantity over all sigma. Yeah. Okay. Yeah. So is this clear? What is a maximum weight perfect matching in a complete bipartite graph where you have weights, right? Okay. Any doubt till now? Okay. So now I will write a tremendous theorem which will just tell me how to solve NV-free Renn division and even how to compute it. Not just, it will give an existence for sure, but it will also tell me how to compute it in poly time. Right. So yeah, okay. So I'll write a lemma first and then go on to describe how do we prove existence and hence computation as well. Okay, so the lemma says that, okay, I've been given a Renn division instance, right? And so I look at the, given the Renn division instance, I can construct a valuation graph, right? Because I'm being given all those base values. I'm telling you, compute a maximum weight perfect matching in this particular valuation graph. And what the lemma asserts is that for this particular maximum weight perfect matching, you can always find a price vector such that the tuple, let's say sigma star comma p star, will be NV free. So what, this is a very strong result. It says that, okay, any NV free allocation, you take any NV free allocation, let's say sigma star comma p star. This particular allocation sigma star must be a maximum weight perfect matching in the corresponding valuation graph of the given Renn division instance. Okay, yeah. I'll formally write what the lemma is, and then we'll do the proof as well. Yeah, but it's remarkable, and it's one needs to see that, okay, you don't even need to touch the price vector, and then you can decouple this sigma star and p star in this tuple and just say that, okay, I know that if this tuple needs to be an NV-free Renn division, the assignment of this sigma star must be a maximum weight perfect matching in the corresponding valuation graph. I don't even care about what p star is. I know the characterization on sigma star, which is a very strong result. Okay, so formally, let me write the lemma. So let's say for any Renn division instance, Q, so it comes with a set of agents, set of rooms, and the utility functions as well. And right now we are considering quasi-linear utility model. So for any Renn division instance with quasi-linear utilities, So, which means that, okay, so, so the lemma says that for such a N division instance with by which where you have quasi-linear utility model, an allocation sigma, can be coupled with a price vector to realize an envy-free solution if and only if sigma is a maximum weight perfect matching in the valuation graph. And valuation graph is being constructed the way I have described. It's a complete bipartite graph with weights on the edge AR, nothing but this particular base value VAR. Yeah. So again, this is a very, very strong result which says that, okay, any allocation sigma can be coupled with a price vector only also to obviously to realize to make it an envy-free solution only if it's a maximum weight perfect matching in the valuation graph GQ. And again, if and only if the other way around says that, okay, if you're given a tuple sigma comma p and someone claims it that it's an envy-free solution, this particular allocation sigma must be a maximum weight perfect matching in this graph GQ. Okay, is the statement of lemma clear? Any doubt in the statement? Yeah. Okay, so let me do the proof. Okay, so one thing I'll assume right now, which I'll circle back to it if I have time, but note that, okay, given any graph, given any complete bipartite graph, one can in polytime compute a maximum weight perfect matching. Okay, the polytope, the LP polytope is integral, and we can see the nitty-gritties of it. But let's see, assume that, okay, first of all, we know that a maximum weight perfect matching can be in polytime computed for a given complete bipartite graph. Okay, it comes via linear programming. You just write a linear program and it's an integral polytope. And also the existence of price vector, if you guys know, like primal dual. Okay, so let me just assume this particular thing for now. So you write an LP for computing this max weight perfect matching. So let's say you write an LP and then there's some notion as a dual LP. You write the dual LP, and so what I'm saying is sigma star will come from here and the dual variables will correspond to the price vector P star. So the existence of envy-free solution anyway comes from a LP duality argument. We can circle back to it, or we can take it offline if you want to know what this is. But okay, right now I'm assuming existence. I'm assuming existence and proving this particular characterization of sigmas. Okay. Okay, so how does this proof go? So let me prove the if part, which is this particular part. Okay. So what am I assuming is, let sigma p be an NV-free solution. And I need to prove that sigma is a maximum weight perfect matching for this graph GQ. Okay. Yeah. So for contradiction, uh, okay. Okay. So let us assume that sigma p is an NV-free solution, and let's say some other matching pi be a max weight perfect matching. Perfect matching of the graph GQ. So what I'll show is that pi comma p is also an NV-free solution. So in a way, what I'm proving is, you take a maximum perfect matching pi, it can be coupled with a price vector such that pi comma p becomes an NV-free solution for the same instance Q. Okay. So I'm assuming that pi was a perfect weight, pi was a maximum weight perfect matching. So what can I write since it's a perfect, okay. So, okay. So I know that the weight of this particular matching pi has to be maximum, right? Since it's a maximum weight perfect matching. So so I can write that VA of pi A summing over all agents. This particular value is the weight of matching pi, right? So I know that since I assume that pi was a maximum weight perfect matching, I know that its weight must be at least the weight induced by the matching sigma, right? Yeah. Remember that I've assumed sigma comma p is NV free. So sigma is some matching. I want to show that given a maximum weight perfect matching, it can be coupled with a price vector to make it a NV free solution. So my goal is to show that pi comma p is again an NV free solution. NV free solution, and I've assumed that pi is max weight perfect matching. Okay. So this particular first step, the first inequality is clear, right? How did I get it? Since pi is the maximum weight perfect matching. So what I'll do is, so this is some jugglery what I'll do. I'll just subtract the p. So this is the p, right? I'll subtract it from both sides. So what I'll get is sigma a minus, I'll subtract this particular price from both sides. So this particular quantity is obviously equal, and I've just subtracted from both sides. Okay. And then what I'll do is, I'll just regroup these quantities in a particular way, which is quite intuitive. How should I regroup? So what I'll do is, I know that this particular agent A is getting sigma A room. So I'll just regroup it as V of sigma A minus P sigma A. and then sum it over all agents A. So why this particular quantity is equal to this particular quantity? Why can I regroup in this particular way? Yeah, so since sigma was a matching, there were like, here were just price vectors written over here, like price of room 1, 2, 3, 4, 5, 6, and then I just coupled it with the room agent A is getting, right? So these two quantities are exactly equal. I do the very same thing here as well, so I minus P of pi A, right? So these two quantities are exactly equal. I've just regrouped things, and these two values are again exactly equal, and because I've just regrouped. So now, since we had assumed that sigma comma p is NV free, can someone tell me what would be the next argument? Remember, sigma comma p was NV free, and therefore I have this particular inequality that the utility agent A is achieving from room sigma A under the price P sigma A is at least the utility he is achieving from any other room R, right? Remember, this is true since sigma P is NV free. Yeah. So what do I get if I observe this particular thing and try to apply this observation to this particular inequality? Okay. Okay, till now it's all clear, right? Whatever manipulations we have been doing. They may be different, yes. Yes. Exactly. Yeah. Exactly. So what she's saying is, what I'll do, so this constraint is true for all rooms R, right? I'll just apply this particular constraint for agent A on the room pi A. So on the room he is getting under the bijection or under the matching pi, right? So if I do that, I know that VA of sigma A minus P sigma A, this must be at least VA of pi A minus P pi A, because pi A is some room R, right? So this should be true because it was true for all R, it should be true in particular for the room pi A, right? And pi A and sigma A can be equal, no worries, but they can be distinct rooms as well. We have equality anyways, right? So here you have, let's say you have these summations here. So this is, let's say, for agent A1, this is for agent A2, A3, let's say we have 3 agents. This is for, again, agent A1, A2 and A3. This is what he is getting under pi matching, and this is what he is getting under sigma matching, right? So I know that just applying NV freeness term by term, I will indeed get this particular equalities. So VA sigma A minus P sigma A must be equal. So I know I have the inequality here, but it would be exactly equal to VA of pi A minus P pi A. This will happen for all agents A. Right? This last step is clear, right? So I've done nothing, but I just observed that since sigma p is NV free, this particular tuple is NV free. I know that I have this particular inequality, and therefore this inequality must prevail here as well. And in particular, this is not an inequality but an equality. Okay, so note having this particular equation for all agents, what can I conclude now? So what can I conclude about the allocation pi comma p? So okay, I have this particular equation for all agents, right? So what can I now conclude about the allocation pi comma p? Exactly, it also must be NV free, because just let me write it again. So what I had it, this is exactly the utility is achieving under another matching, which is a maximum weight perfect matching. This is happening for all agents, right? And I know that this particular quantity was at least VAR minus PR. So, okay, yes. Yeah, okay. So I have this particular equality from last argument, and I know that this holds true since sigma p is NV free, right? So in particular, I know that pi comma p will also form an NV free solution. Yeah. So in particular, what is happening is, give me any max weight perfect matching of the graph, of the valuation graph GQ, which is, let's say, pi. I can couple it with a price vector such that it will indeed form an NV free solution, right? So is this part clear? So let me reiterate what in this particular part I am saying, that give me a random division instance Q, construct the corresponding valuation graph GQ, and then compute a maximum weight perfect matching pi in it. I am showing that you can always couple it with a price vector such that it will be NV free for the same instance Q. Right. So what is left for completing the proof of the lemma? It is the other way around, which is only if part. Only if part says that, okay, you start with an NV free solution, let's say sigma comma p, and then you need to show that sigma must be again a max weight perfect matching in the valuation graph GQ. Yeah. So in the other way around, what I need to show that, yeah, let sigma comma p be an NV free solution. I need to show that sigma is a max weight perfect matching in the corresponding valuation graph GQ. Note that in the previous part we showed that given a perfect matching, maximum weight perfect matching, I can couple it with some price vector to make it an NV free solution. Right now I am showing that, okay, give me an NV free solution, I will say that this sigma has to be a maximum weight perfect matching and cannot be anything else. It cannot be a suboptimal perfect matching, for instance, yeah. In the previous part, yeah. Yeah, that's what I was, that's what I assumed here, that it does exist. It comes from LP duality, and I wanted to cover it, but I don't have much time. We can talk about it offline, yeah. Or maybe I'll cover it tomorrow. Yeah. So right now, do assume, let's say, NV-free solutions exist under quasi-linear model, and and I'm just proving this particular property or characterization of NV-free solutions, where I'm saying that this particular if sigma comma p is an NV-free solution, that sigma has to be a maximum weight perfect matching. It cannot be anything else. And give me a maximum weight perfect matching, I can always find a price vector so that the tuple sigma comma p would be an NV-free solution for the given instance q. Yeah. Yeah. Come on. Okay. Oh, no, okay. So, okay, so the proof of this particular existence is indeed coming. So, okay, here I'm assuming the existence, and then separately I can show the existence via LP duality, and then this particular lemma is just giving a characterization on those sigmas. It's not giving me, it's also giving me how to compute it, because I can compute a maximum weight perfect matching in poly time and then write an LP, and in that particular LP, the NV-free constraints would be a linear constraint given the maximum weight perfect matching. Okay, I'm being vague because, yeah, I've not gone into LP duality at all. Yes. Okay, you just solve the LP, it gives you the solution there. No, okay. So this is a lemma which is telling you about a characterization of these solutions, and an existence can come from LP duality. This is just a characterization of NV-free solutions. We can like take it offline if there's any more confusion, right? Okay. Right now, what I'm trying to prove is a characterization of these sigma comma p tuples, which let's say is NV-free. The sigma must be a maximum weight perfect matching. It cannot be anything else. I know that I've assumed existence right now, but currently I'm just trying to say that, okay, assuming existence, I am proving this particular this. Okay, the existence can also come from a combinatorial lemma, which is a variant of Sperner's lemma, and it can also come from, which is called KKM lemma, and existence can be shown from other methods as well, but this is a simpler one. That's it. Yeah, I know it might be a roundabout way of saying whatever, but you can also always assume that the existence is coming from another combinatorial lemma, which is called KKM lemma, and then I'm just trying to prove a characterization for NV-free solutions, and then having this characterizations, I can always compute an NV-free solution as well. Yeah. Okay. Hmm. Correct. Maximum. Hmm. Correct. Okay. Yeah. Okay, to complete the characterization, now I need to show is, give me any NV-free solution, the, the matching of the bijection sigma must be again a max weight perfect matching. Okay? Yeah. So the proof is via contradiction. For contradiction, assume sigma is, let's say, not a maximum weight perfect matching. For contradictions, suppose not. So which means that there exists some other max weight perfect matching, and let me denote it by, let's say, sigma star. Let's say sigma star is a max weight perfect matching, because if sigma is not, someone else would be. Okay, so I should go to next page. Okay, so I know that I have two things, sigma comma p is given to be NV free, and I've assumed that let's say for contradiction sigma is not a maximum weight perfect matching, and let's say some other matching, let's say sigma star is maximum weight perfect matching in the graph GQ. Okay. So if it's a maximum weight perfect matching, I know that this in particular is true, that the weight of this particular matching sigma star must be greater than the weight of the matching sigma, because sigma is not a perfect matching, right? So this is the weight of the matching sigma star. I know that this has to be strictly greater than the weight of matching sigma, since I've assumed that sigma is not a max weight perfect matching, right? So there's a strict inequality going on here. Yeah. So the proof is almost the same. I again do the trick of subtracting p, or subtracting the summation of PRs from both sides. So this minus summation of R PR is strictly less than the summation of VA sigma star A minus this particular quantity. So I've subtracted this quantity from both sides, strict inequality prevails, and I do the same trick again. I regroup the terms, by which I mean that, okay, this goes with this, and again strict inequality, and regrouping the terms, and therefore sigma star A has price P sigma star A, right. Yeah, I've done nothing new till now, and so I need to reach to a contradiction, and the contradiction one can feel that it would be contradiction to the NV freeness of sigma p, right? So can someone complete the argument for me? Like this is, I have this particular inequality, strict inequality going on, and I want to derive a contradiction, right? Because we are doing this proof via contradiction. I have assumed that sigma here is not a max weight perfect matching, and so what is the contradiction here? Exactly. So since you have strict inequality here, there must exist at least one agent, let's say A only, agent A, such that something like this happens, VA of sigma star A minus P sigma star A. This thing is strictly greater than VA of sigma A minus P sigma A, right? And this contradicts the NV freeness of sigma P solution, right? This particular thing contradicts, which is a contradiction, and in particular contradicting the fact that sigma P was an NV free solution to begin with. It is contradicting the NV freeness for agent A in particular, right? Yeah, here he is getting strictly less utility than the utility he is deriving from the room sigma star A. Yeah, and this completes the proof, right? So what we've seen is a characterization of these matchings which can coupled with a price vector to form an envy-free solution, right? Yeah. So give me any Renn division instance. Yeah, give me any Renn division instance, and with quasi-linear utilities, I know this characterization of, I know the characterization for envy-free solutions, right? Yeah. So sigma comma p is envy-free if and only if sigma is a maximum weight perfect matching, is a maximum weight perfect matching in the corresponding valuation graph GQ, right? So this is a characterization, a very, very strong characterization we have under the model of quasi-linear utilities, right? Okay. Yeah. And as he has mentioned that this particular lemma tells you how to compute each and every possible sigma, each and every possible envy-free solution, right? You just compute a maximum weight perfect matching in the graph GQ, and then we'll see how via LP duality you can come up with a price vector as well. Yeah. In particular, price vector is the solution of the dual of the LP you consider for maximum weight perfect matching. Yeah. And again, since maximum weight perfect matching can be solved in polytime via linear programs, and the dual of that linear program, if you write, has linear constraints, you can again solve it and you can show it that the dual gives you price vector, and hence in this particular model of Renn division instance, computing envy-free Renn divisions is efficient. Like you can in polytime compute an envy-free solution under the model of quasi-linear utilities. Yeah. Okay. I did want to do the LP duality, but let's see if we get time. Yes, tomorrow we can have a look at it. Yeah. Any questions with this particular model of Renn division? Yeah. Okay, then I'll stop. Yeah.